Hey everyone, it is that time of the week again for our live conversation where, as part of your daily equation, I'm happy to cover anything that is equation related. And of course, since equations are related to everything, that means everything is game. So truly feel free to ask me about anything that's on your mind. You know me, if I don't know the answer, I'm straightforward. I tell you. If I have something to say on the subject, I'm happy to offer it. And let's begin as we sometimes do. And I see Luis has already noted that he is in our conversation from Mexico, but I do like to see the various places where everybody is from. So if you don't mind just sort of saying where you're from, I would love to see that. And then as those countries roll by, I will be all too happy to start finding the first questions and get moving on things. All right, so what do we have here? What am I going to begin with? Well, there's one question I really want to begin with, and I didn't have a chance on YouTube to locate who it was that asked it. But somebody asked in one of the last two sessions about what it means when people say that time is curved, right? In the general theory of relativity and special relativity, too, of course, we know that space and time are all together, they're blended into this uniform continuum that we call space time. So if we learn that space is curved in the general theory of relativity, then we must know that time is curved too. But we all have an image for what curved space is, but what does curved time mean? And the answer to that is less mysterious than it sounds. It's not like you have a Dolly-esque like clock that sort of warps time in some literal spatial way. Of course, a clock is warped in space, it's not itself warped in time. But when we say that time is warped, we simply mean that the rate at which time passes at different locations need not be the same. And in particular, what we learn in the general theory of relativity is that if you have a massive body that exerts the force of gravity or curves the environment around it, the space time environment, what that means is the closer you get to that body, the slower clocks tick. So if you had a clock, say, that is at the top of the Empire State Building, you have another clock on the ground floor there at 34th and 5th Avenue, whatever the right address is, I think that's correct. Then the clock at the top of the Empire State Building will tick off time a little more quickly than the clock at the bottom of the Empire State Building. So time is warped in that sense. If you have a ruler that's warped, then different parts of the ruler will measure different distances between the same two locations, right? That's what a warped, non-uniform ruler would do. If you have time that's warped, then clocks will not measure the same elapsed time between two events by virtue of this warped or curved nature of time. Now, for the example of the Empire State Building, you'd say, well, why don't I know about that? The reason, of course, you all absolutely already know as well. The amount of time warpage, time curvature between the top and the bottom of the Empire State Building is tiny, tiny, tiny fraction of a second. We just don't notice it. But if you took that same example and you put the Empire State Building at the edge of a black hole, then the clock near the edge of the black hole, closer to the source of gravity, would tick off time far more slowly than the clock farther away. And that would, in principle, be a measurable time difference, right? I think as mentioned before, in Interstellar, you saw that example directly as the astronauts that went down to the planet that was closer to the black hole than the crew member who stayed up in the ship. They just spent a couple hours in that environment, but time is ticking off so slowly for them, so quickly compared to the clock on the mothership, that when they returned to the ship, their fellow crew member had aged like 20 years, where they had only aged a couple of hours. So that's what we mean by curved time. All right, moving onward. What else do we have here? So Salim Yagi says, Dr. Green, thank you for amazing words. Is it scientifically correct to say that gravity is due to a field property of space-time, or is it just pure objective geometric property of space-time? And it's a very good question because we physicists freely go back and forth between the language of a gravitational field and the language of the geometry of space time. And I would encourage you to feel comfortable going back and forth between those languages as well. In fact, you should feel comfortable using the standard Newtonian language as well, where you talk about a force of gravity, one object pulling on another. Because depending on the problem at hand, one or another language can give you the greatest insight. Einstein's general theory of relativity language is indeed one in which we think about gravity as nothing but the curvature of space-time. So why do objects move in interesting trajectories under the old Newtonian language of the force of gravity? Einstein's answer: they move in these interesting trajectories, these orbits, because they are sliding along these grooves, these indentations, these valleys in the geometrical structure of space-time. So there's a sentence where I use the Newtonian gravitational force language, which is also the Newtonian gravitational field language, and also the Einsteinian geometrical language for the shape of space-time. And so freely move in between those languages as befits whatever situation you are in. Now, let me just give one example, and I'm going to, in your daily equation of next week, boy, it is really windy here. I don't know if you guys can hear this, but in a moment I may need to close down the windows, even though it's quite hot in here. But next week in your daily equation, I'll make this point as well. In the Newtonian description, right, the apocryphal or perhaps real story has it that this apple fell from the tree and it hit Newton in the head. And the Einsteinian description, in terms of the geometry of space-time, is actually quite different because the freely falling objects, in Einstein's view, they are the ones that set the standard of rest. And therefore, in an Einsteinian description, the apple, when it's in free fall, after it detaches from the branch, it's just sort of hovering there in space-time. And it's Newton's head that comes up and slams into the apple because Newton is not in a freely falling frame sitting on the surface of the Earth. The Earth's surface is getting in the way of Newton's free fall. Newton can't fall through the rock of the surface of the Earth, even though his body would like to. So that actually helps us understand the ancient puzzle that you all know the answer to. But why is it that two different objects fall at the same rate regardless of their mass? I could try to do this, but I'll make a mess of it, so I better not. But you know what I mean. You take two objects, I don't want to break the Apple Pencil, then I won't be able to do your daily equation. But I let them go and they both fall together. Why is that? According to Newton, it's because there's a quality between gravitational mass and inertial mass, which means they both cancel out of the F equals ma equation when the force is equal to m over r squared times g. That's equal to m times a. The m's on both sides cancel, so it's only the big mass of the Earth that really determines the acceleration of each of these objects. Therefore, they fall together. But that's a mystery. Why is gravitational mass equal to inertial mass? Einstein's answer is completely different. Einstein says, when you let go of these two objects, I'm not going to do it again, but when you let go of them, they're in free fall from your perspective, which Einstein says sets the standard of rest. Now imagine, therefore, that they are at rest in space-time, and it's the Earth that's rushing up to them. So why do they hit the Earth at the same moment? Einstein's answer is very straightforward. They hit the Earth at the same moment because they don't move. It's just the Earth that comes up and meets them, and the Earth has a singular body. When it moves up to their location, it hits them, and of course it hits them at the same moment. They were just sitting there waiting for the Earth's arrival. So that's the geometrical Einsteinian view, and in that case, it does give us insight that otherwise would be hard to glean. Okay, so what else do we have? Alina says, big fan of your videos. Thank you, Alina. I appreciate that. Abu Bakr Farouqi Greetings, Professor Greene, watching you from Pakistan. Wow, that's great to hear. What is your view regarding the idea that the entire universe is inside a black hole? Well, it's an interesting question. First of all, talking about the entire universe inside a black hole is a bit extreme, but what I would say is it is possible that, at least according to the traditional general relativistic description of black holes, I'm not going to modify it with modern or more recent conjectures, speculations about firewalls and all that sort of good stuff. So let's just act as though Einstein had the important word on black holes, which may not be the case. But if that's true, then right now it's quite conceivable that the Earth just passed across the edge of a black hole, that we are all now inside of a black hole. Why is that? The edge of a black hole, in Einstein's description, is not some special location in space. It's just an ordinary chunk of space that has the unusual property that once you pass that location, the event horizon, you're no longer able to get out. But you don't have any direct physical reaction to crossing over the event horizon of a black hole. And so right now, everything, as we look around the world, we could all be within a black hole. And we'll only really recognize that later on when we get closer and closer to the center of the black hole, because then, depending on our precise distance from the black hole, different parts of the Earth, different parts of our body will feel a different force. If we are going feet first toward the center of a black hole, our feet will experience a greater pull than our head. Our body will be stretched. Spaghettified is the technical term that we use for this process, until ultimately we're pulled apart into our constituent particles that will all rain down on the singularity, whatever that is, the center of the black hole. We don't really understand what goes on there. So in that sense, we could all be within a black hole right now. I'm not exactly sure how to describe that if you want to truly think of the entire universe, but any large chunk of the universe could follow exactly the same process that I just described for the Earth, and therefore, in that sense, we could be within a black hole. Nikhil Tahalani says, hello, Professor Green. I'm a computer science student in India. Boy, a lot of Pakistan, India today. That's fantastic. Recently developed interest in physics because of you. Oh, that's great to hear. It really is great to hear. It's so inspiring to hear that these little videos that I create in this little room here, or other things that we do, actually reach out and affect people. So thank you for telling me about that. Question is, can you guide me if I can do both together, namely computer science and physics, and where I should start? And the answer is absolutely. Number one, the distinctions between computer science and physics have certainly been blurred in the last few years in a substantial way, because one of the dominant interesting problems that people who have been focusing their attention on quantum mechanics for a long time, that they're focusing on, is quantum computing. To really see whether we can inject our understanding of quantum physics into a new kind of computational procedure. Now, look, of course, every computer in some sense is a quantum computer, because the integrated circuit only exists because we can manipulate the motion of tiny particles like electrons, and we need quantum mechanics to understand how to do that. But quantum computing takes that into a radically different direction, not just the technological innards of a computer to be governed by quantum physics, but rather the computational process itself, making use of the full might, the full power of quantum mechanics. Roughly speaking, if you buy into the many worlds interpretation of quantum mechanics, it's as if we're trying to build computers that will do parallel processing of certain kinds of computational procedures across the many universes that quantum reality spans, make use of all of those universes to simultaneously crack apart various parts of an interesting calculation, and at the end find a manner of pulling out the solution that we are looking for from this broad swath of parallel computational procedures. So I don't know if that kind of blending of physics and computer science fires you up, Nikhil. But that certainly is an arena in which you would be well posed to make a contribution by carrying on with your studies in computer science, but also building up your understanding of physics with all the standard things, classical mechanics, quantum mechanics, thermodynamics. You need all of that. And some of that you can learn on your own. So I would look at, wherever you are, the course of study that's available to see about blending these, but it's not as though you're saying to me, I want to dance in the Bolshoi ballet, and I also want to be the next Einstein. Not impossible. And I would actually encourage you if that was your dream. But what you're saying is more easily attainable than that particular goal, that particular dream, because computer science and physics are no longer as far apart as perhaps your studies might suggest that they are. Okay, what else do we have? There's an interesting question here. Uh, oh, here's one from China. Yu Ping Zhang. Hi, Professor. Big fan from China. Thank you, Yu Ping. If I move close to the speed of light relative to you, but from my perspective, you are the one who is moving fast. So in the end, who is getting older? And yeah, Yu Ping, that is a puzzle. It is one that people have kicked around for a long time. We think we understand it quite well, which is that the notion of who is getting older is a question that needs to be framed with greater precision in order to really answer your question. And the real question is, if you and I get back together and we compare our ages either visibly or more precisely with our watches, on whose watch will more time have elapsed? And if it's the case that I say am not experiencing any, say, acceleration during this entire journey, right? This entire journey, I'm just sort of sitting around and I never feel a force on my body. I never feel a change in my speed. But you, in order to come back to me, must feel that change. Let's say you go out in space, you've got to turn around and come back. That turnaround is an acceleration. You will feel it. It is a change in your velocity, a change in the speed and direction of your motion. And that's what breaks the symmetry that otherwise would be quite confusing. And because of that break in symmetry, you feel the acceleration, but I do not. Then it turns out that you can establish that you are the one that is going to be younger on the return. I will be the one who is older. It is your watch that will be ticking off time more slowly. Now, you might say, that feels like we're relying too much on acceleration to address the issue. And indeed, there are other versions of the story. You could go out into space, and rather than literally you turn around, imagine that you've worked out with a friend of yours, a partner in crime, that they are heading toward me and they set out on the journey in just the right way, that you and your friend pass each other and you're able to hand off your watch to your friend, and your friend brings that watch back here. So no one's accelerated in this case. You never turned around, you came back, your friend didn't accelerate, they were always traveling toward me. What happens in that circumstance? And the answer is a little bit different. During the handoff between you and your friend, that is a change in frame of reference, which actually changes your perspective on what events are happening simultaneously at the same moment. And if you take that into account, there's a jump in time between what you said was happening at the same moment, and what your friend says is happening at the same moment. And that also comes to the exact same conclusion. If you want to see this done fully and visually, obviously there's just so much I can do in explaining things on the fly right here. But I have a whole course on the special theory of relativity. There's a math version of it. There's a visual version of it. You can look at these courses, take these courses for free at worldscienceu.com. That website is being relaunched, refreshed. I think it's still available right now, but if it's not, within a week or two, it will be available. And toward the end of that course, there are like 44 modules, a lot of content in there. But I show you visually what it would look like in sort of any scenario of the twin paradox that would come to mind. And so the short answer is, I will be the one who is older if I didn't accelerate. The long answer is go check out all the details on World Science U. I think you would enjoy doing that, and that goes for any of you who want to see special relativity done in a highly visual as well as mathematical way. Okay, what do we have here? Um, Hello, sir. Asit Dash says, "You are my inspiration. Thank you. How in string theory is it that the vibrations give rise to new kinds of particles?" And yeah, that is the basic idea in string theory. And let me just explain the essence of it. So, in string theory, we imagine, at least in the most vanilla bread and butter approach to string theory, people have gone in many different directions with these ideas. Let me just give you the dominant way that people have thought about things for a long time. If you were to take an elementary particle like an electron or a quark, and somehow were able to magnify it to an extent that you could see its most deep inner structure, you'd find that each of those particles is composed of a vibrating filament, a one dimensional vibrating filament. And you might say, how could particles as different as an electron and a quark, they've got different electric charges, they respond to the strong nuclear force in different ways. How is it that a string can distinguish them? And here's the idea, and I'll focus on mass, as that's the easiest example, easiest quality for me to talk about. The mass of a particle in string theory comes from its energy, right? Einstein taught us E equals mc squared, the most famous of all equations, the equation I started with a month ago in this series of Your Daily Equation. Let's turn that equation around, actually turn it around in the way that Einstein himself wrote it in his September 1905 paper. He didn't write equals mc squared. In fact, he used different symbols, but put that to the side. Instead, he wrote m equals e over c squared. M equals e over c squared. So mass comes from energy divided by c squared. So if you want to know the mass of a particle that emerges from a vibrating string, you find the energy of the vibrating string, divide it by c squared. So how do you get two particles of different masses? You get two particles of different masses by having two strings vibrating with different energies. One is vibrating slowly, if I can use ordinary language. One is vibrating more vigorously, faster, greater energy, greater mass. So that's the way that a one and the same ingredient, the same vibrating filament, it's not like you've got different filaments, or the same species of filament, but if they vibrate in different ways, you get different masses. Now, to describe different electric charges is a little bit more subtle. That would take me pretty far afield, but it's qualitatively no different from that. It's just there are more exotic qualities of a vibrating string that correspond to charge. And if it's vibrating in one manner, in those qualities, it'll yield one charge. Vibrating differently will yield a different charge. Okay, what do we have here? Ali Unisayan asks, how should we study to be a good physicist? Please specify. Brian, is very important to me. Sure. Look, the most important thing, if you're asking me, when you're in the learning phase of physics, is that you don't get distracted by things that are happening at the frontier of research and think that you can jump right to the edge of understanding without slogging through all of the basic foundational material. I can't tell you the number of students that come to me and they just say, "Hey, I'm ready. I just want to work on string theory. Or I want to work on black holes, or I want to work on the Big Bang." I mean, it's exciting for me to hear the interest in working on those subjects. But the fact of the matter is, if you don't understand classical mechanics and quantum mechanics and differential equations and thermodynamics and statistical mechanics and special relativity and general relativity and quantum field theory, and on it goes, the traditional undergraduate and graduate curriculum, if you don't have that solidly under your belt, it's going to be very hard for you to contribute. So, although it may feel that that material is old and you don't really need to know that material, the fact of the matter is physics is a very hierarchical, vertical subject. The things that we work on today rest upon the things that we learned yesterday. And by yesterday, I mean everything from truly yesterday back to a few centuries ago. So the answer is you just need to work day and night to learn the basic material. And it's not just a matter of reading it, it's a matter of doing problems upon problems. You need to gain a facility with putting the material into action. So it's a lot of hard work, but the payoff is significant. Number one, you understand the material so much better when you work through it. Every equation you understand, every problem in the book you can solve, but it then prepares you for bringing all that knowledge to bear on cutting edge research. And that's really the way to get there. There's no shortcut, unfortunately. Goran Kohler asks, how do you balance life and work? Well, you should ask my wife and kids. Not well all the time. Sometimes I do it better than others, but I kind of work all the time. I kind of work 7 days a week. I don't come to Saturday and Sunday and say, oh, it's over. I don't have to think about things until Monday. And, my family has come to accept that. Perhaps the reason is my wife and I both are the folks who started this World Science Festival, which is the rubric under which this Your Daily Equation and many other things sits. So because we work together on this, it doesn't always feel as though I am leaving the family conversation if I'm working on things, at least in this regard. My kids get a little bit tired of the fact that my wife and I both work a lot all the time. So yes, the balance is not always there, but I certainly have found the ability more now than say 20 years ago to pull away from either doing a physics research project or writing a book or doing this kind of an activity to spend more time with kids. And I have to tell you, it's the most important, the most vital thing to do. And this pandemic only brings that home even further. In the end, what really matters are the people you spend time with and the people that you affect and the relationships that you have, because in the end, everything just evaporates into the void. It doesn't mean it's not important to strive. It's not important to understand the universe. I'm driven to do that. But in the end, what really matters are the relationships. And it's hard to keep that in mind, but it's vital to do so. All right, what do we have here? Cosmic Slice. I'm going to miss the World Science Festival this year. I love volunteering at it. Yes, I agree. We're going to do a kind of World Science Festival this year. We're not going to do it like all at once in a 5-day period as we do when it's a live event. We will roll out a series of programs over the coming months. Some of those programs will take place right in this space right here. Others, we have other ideas up our sleeves for what they will look like. But from that perspective, unfortunately, volunteering is not something that is relevant with the way the world is at the moment. But the programs themselves, they will be coming. So at least that side of it will carry forward. Professor Greene, Divyesh Raj asks, what to do when your school interferes in your education? That is an encapsulation of a quote of the man himself, Albert Einstein. And I appreciate that reference. Einstein said the only thing that interferes in his learning was his education. But Einstein was Einstein. Einstein was the kind of guy who could go off and read the greats of physics. Read Maxwell's original works, read Kirchhoff, read Lorentz, read Planck, and not only digest what they were talking about, but be able to take their ideas to the next level. Unfortunately, most of us are not Einstein. Would I love to be at the level of an Einstein? Yeah, I really would. How exciting to be able to revolutionize our understanding of things. But you come to terms with the limited capacities that you have in any domain. And for most of us, that limited capacity means we do have to be educated. Most of us cannot just do the Einstein thing or do the Ramanujan thing where we can just learn on our own. That would be great if we could. And if it works for you, fantastic. But for most of us, the education process doesn't interfere with the learning. It's part of the learning. I hope you guys are not distracted by my dog, who seems to be barking outside the window. That probably is because my dog Luna has a different perspective on learning and education and understanding and wants to chime in. But, Luna, you want to say something, get your own damn show. This is my show. Okay. So I'm just going to say my view on learning and education. No, Luna, if you have anything you want to say, feel free to chime in again and I'll try to interpret for the audience. Okay. So Mohammed Zuneho asks, Dr. Brian, in thermodynamics, we have something called a closed system in which only energy can be exchanged, not matter. Isn't it against mass energy equivalence? Well, the the usual way that we do thermodynamics, and I hope I'm interpreting your question correctly. If not, feel free to ask it again if I misinterpreted it. In thermodynamics, there are two ways in which we formulate the theory. When we apply the equations to a closed system, we really mean that it's really closed in the sense that it's not interacting with the environment around it. All the stuff, all the energy, all the mass, it's all staying within that environment. The alternative is when we look at an open system, and an open system freely can exchange things with the environment. Now, you're right, in certain circumstances, we only allow certain qualities to be exchanged. But the real reason why we distinguish between a closed system and an open system is for a closed system, we can argue that the entropy will not never go down, but is highly, highly unlikely to go down. Whereas for an open system, entropy can leave. It can be expelled with the stuff that you are allowing to cross the border, the open border, if you will. And therefore, for an open system, entropy can go down. And of course, when I look at myself, I am an open system in the sense that I'm constantly emitting entropy to the surroundings, heat, waste going outward. And that allows my entropy to not continually increase, which would not be good for my health. So the way I keep my health, the way I keep myself intact is through my interactions with the environment, allowing myself to be an open, not a closed system. And that openness is what allows my entropy to seemingly thwart the second law of thermodynamics, but of course it doesn't, because if you take account of the entropy that I release to the environment, then with that contribution, the overall entropy of me and the surroundings does go up. Okay, what else do we have here? There was an entanglement that just went by me and I missed it. Here it is. Oh, Prayag, why are particles entangled just by interacting? And it's not enough that particles interact to have the kind of entanglement that, for instance, I used in your daily equation in describing entanglement. That was so-called maximal entanglement, where I had these two particles, one was spinning up and one was spinning down. You remember how that goes. And that state of affairs will not generally be enforced by simply two particles interacting. The way you get those kinds of entangled particles is, for instance, you take, like, one example is you take a calcium atom and you excite the calcium atom. Maybe you shine some laser light on it. As the calcium atom falls back down to the less excited state, it releases energy in the form of photons. And one way that it can release that energy is giving off back-to-back photons. And those back-to-back photons will be analogous to the spin up and spin down electrons. They will be maximally entangled. They will have an overall zero angular momentum state, even though each of them can have some spin angular momentum. And those spins will be correlated in such a way that they mimic what I was describing with the entangled electrons. So in that case, it's not that the photons interacted to become maximally entangled. Rather, the calcium atom is the unique common starting point. And when it reduces to its less excited state, it emits these particles. It creates these particles in this maximally entangled state. Tyden says, God, I love science. That's an interesting sentence. I love that. God, I love science. I'm not sure how to fully interpret it, but it seems to have a good feel to it. Let's see. What do we have here? Um, what do we um uh Susan Van de Ham. Susan Van de Ham. Ah, I got that. AKA Primordial Soup. Do you think there really is an end to smallness? Do I really think there's an end to smallness? So I gather what that question is. You know, the progression of the history of sciences, you got stuff, macroscopic, bulky stuff. You look at it, sufficiently powerful microscope, or you dissect it, you get to molecules, you get to atoms, atoms, you get to electrons around the nucleus, the neutrons, the protons. Inside the neutrons and protons, you got the quarks. If string theory is right, and we don't know that it is, you keep on going, you get to the strings. The question is, does it keep on going, or is there an end? And we don't know the answer to that. My guess is that there is an end. I don't see any reason why this chapter of exploration needs to go on forever. It could well be that the universe truly does have some fundamental, indivisible, uncuttable elementary constituents. Do we have those in hand? It's possible that we do already. It's quite possible that we do not. However, the motivation for thinking that this journey will go on forever is one of pattern. The pattern is that we have always found smaller stuff inside of bigger stuff, but I don't see any fundamental reason why that pattern will persist indefinitely. So if you ask me for my guess, and it really is just a guess, my guess is that there are fundamental entities that will not admit a finer level of structure, and there are fundamental laws that govern how those fundamental entities behave. Now, it's interesting, you know, somebody the other day challenged me on my use of govern in a sentence like that. Do laws govern how the particles behave, or do the particles just do what they want to do? And we have these mathematical laws that seem to be pretty good at describing what they are doing. And you know, what's my view on that? My language, certainly my language is I tend to use the word govern because I really do, how should I say it? I really do think that even if we don't have the fundamental laws in hand, my view is that the universe is lawful. It's an assumption, but it's an assumption that seems to resonate well with everything that we have so far discovered about reality. That there are laws, and those laws are unbreakable. And if you have unbreakable laws, it feels to me, it suggests to me, it seems to me that you are justified in thinking of those laws as governing what happens, because the particles cannot simply do whatever they want to do. The particles only execute behaviors that are compatible with the fundamental governing laws. So that's my, in some sense, view of the fundamental nature of reality, fundamental nature of the world. There are some elementary things that can't be divided further. There are some fundamental laws that are in control of the behavior of those entities. The entities don't have a mind of their own in the sense of they can say, well, the fundamental law says X, but I'm going to do Y. First of all, that sentence doesn't really even make sense. But more importantly, it's not compatible with our understanding of how the particles that we do have control over actually behave. So yes, the idea of laws governing stuff is the view of reality that I think is the right way of thinking about things. Can I prove that? No. Can anyone prove otherwise? No. The only data suggests that that is the right way of looking about things. So it feels to me like it's a reasonable way of describing reality. So Fella Super says, hi, Greene. Greetings from Norway. Doesn't quantum entanglement break the principle in special relativity that simultaneity is relative? It actually does not. I understand your thinking on that. You know, if you have distant particles and they're very far apart, and if you measure one and I say instantaneously the other snaps out of the haze of up and down, I'm saying, well, that's simultaneous. But what I really mean, it's simultaneous from one perspective, from one frame of reference. Let's imagine that these two particles are not moving relative to me, this frame of reference that I'm in. Then the action that I'm talking about is simultaneous in this frame. But if you, Fellas, super, are moving relative to me, then you would tell a different story of what happened. If you're moving relative to me in one direction, you will say one particle snapped out of the haze first, and then the other snapped out. Those events would not be simultaneous for the very reason that you said, that simultaneity is relative. And if you're moving in the other direction, you will say the other particle snapped out of the haze first, and then the second particle snapped out subsequently. So, depending on your frame of reference, your description of what happens in the measurement of an entangled pair will be different. The point that I'm making is there is a frame of reference in which they happen simultaneously. And that means, and let me just stress this so that you can be no confusion here. You might say, well, if one snaps out first and then the other, why can't we describe it in terms of a signal from one to the other? But bear in mind that if you have two particles snapping out simultaneously, they're so-called space-like separated, which means that even though the events may appear to have a chronology, one happens before the other, depending on your frame of reference, you will never have a frame of reference in which there's enough time between one snapping out and the other for a signal to travel between them. So everybody and his brother and his sister will agree that there's no way that a signal could go from one to the other to explain one snapping out and then the other. Some will say that they happen simultaneously, others will say that they don't happen simultaneously, but everyone will agree that you can't explain it with a signal traveling less than or equal to the speed of light, going from one after it snapped out, alerting the other, and then it snaps out. That explanation, everyone will agree that that explanation fails. Okay, so Kella Neves says, from a big fan in Brazil. Well, thank you. I'm more than happy if you just want to chime in with comments. You don't have to only ask questions. Thank you. Bogolubo's edge of the wedge theorem asks, what type of mathematics have you used, but you were surprised that it is helpful in this case? Well, yeah, I give you one concrete example. It goes back a number of years, but it was among the most exciting. Years ago, I was working on properties of the extra dimensions in string theory. You know that string theory requires 6 or 7 extra dimensions, depending on how you count, how you describe it. And I became interested with a couple of colleagues, David Morrison and Paul Aspinwall, on whether the fabric of space might be able to rip, to tear. And to address this question, we found that we had to invoke some fairly esoteric mathematics from algebraic geometry and from a fairly esoteric, at least to me at the time, way of representing geometrical surfaces that naturally emerge from algebraic geometry. And with that description, we were able to get a sharp mathematical understanding of the fabric of space, and we're able to show that it can actually rip apart. You may have read about this if you've looked at the Elegant Universe in, I think it's chapter 11 or 10 or something like that. It's too long ago now. Oh, by the way, I'm actually planning on coming out with a new version of the Elegant Universe for the one or two of you who may have read that book. And it's going to have an update. I'm not going to change the chapters that exist, but I'm going to update the book, bring it right up to the present. So for the 25th anniversary, which is in 2024, it's hard to believe it's 25 years ago. But for the 25th anniversary edition of that book, I'm going to add some chapters so you can catch up on things that you might not have read elsewhere, which would be kind of fun. But that's the answer to your question, Bogolubov edge of the wedge theorem. That was an example where some pretty high-powered math and algebraic geometry turned out to be the right language for discussing the ripping of space. Campus Cryptid writes, hell yeah. I'm not sure what hell yeah refers to, but hopefully it was something that I said that you were so excited about that you were moved to write that. Let's see what we have here as well. I'm going to go to this other list from Twitter for just half a second, just so I mix it up a little bit. What do we have here? Nikita Geico asked, tell me if I'm wrong, that most of the current mass and energy in the universe was condensed from the inflaton field after a tremendous expansion. So the total energy of the universe increased. Does this break the first law of thermodynamics of energy conservation? And you're not mistaken, Nikita, in your description. So let me just even put some numbers into the inflationary theory. The inflationary theory shows that you can have a little tiny region of space, roughly say 10 to the minus 26, 10 to the minus 27 meters across. So it's really tiny. It can be filled with, roughly a few ounces or a couple pounds worth of inflaton, or maybe I should talk about kilograms for this international audience. So it could be filled with, grams or kilograms worth of the inflaton field. So not a lot there. And as it swells from the repulsive push of the inflaton field, that region of space swells enormously. As it swells, the inflaton field continues to fill that region of space. So you may have begun with, say, a kilogram of inflaton field, but if the size of the space grows by a huge factor, then the amount of inflaton field filling it also grows by a huge factor. So then you might say, well, where does the energy come from? Because now you've got more because the region of space is incomparably larger. And the answer that we typically give to that, well, there are two answers you could give. One answer that's not really satisfying you could give is that the conservation of energy has to be carefully thought through when you apply it to the universe as a whole. And whereas you can have local energy conservation, turning that into a global statement can be challenging. If you looked at the episode on Noether's theorem that we had, and less people looked at the episode on Noether's theorem, which makes me think that you actually overall don't really like the technical mathematical equations as much as you do the discussion of the big idea. So tell me if you disagree with that, because my temptation is to do more of the big ideas if it appeals to more of you, but that's a sidelight. In that episode on your daily equation, I showed how you get global conservation laws from symmetry, but that was applied to a system within the universe. If you're looking at the universe as a whole and you think through the steps, there's some subtleties that don't always go through depending on the precise shape, the topology, the geometry of the universe. But anyway, I didn't think that answer would be particularly satisfying, so I just put that out there as an interesting point. The answer that I think you'll like better, Nikita, is the following. You may recall that gravity can have and typically does have negative energy. Remember when you learned about gravitational potential energy in physics 1? What is the gravitational potential energy? It goes like minus gm over r, right? If you have a mass m, and that's a negative in front. So when r goes to infinity, say a little test particle would have zero potential energy, but as it comes in, it's in a gravitational field, giving rise to a negative potential, minus gm m over r, second m, the little guy over r. The importance of that is the following. A negative number, it can go arbitrarily negative. So as the inflaton field, as its energy is going up and up and up, filling more and more space, the gravitational potential energy is going down and down, ever more negative. So there's a balancing that can happen there. So it may look like there's more energy because the space is bigger and it's filled with the inflaton field. But if you account for the negative potential energy of gravity becoming ever more negative, they cancel each other out, allowing a kind of energy conservation still to hold. So that, I think, is a more satisfying answer. Nikita, if you're actually watching the live, chime in on the live feed, and I can get a sense of whether that addressed your question. Let me go back to the live YouTube chat and see what else we have here. Let's see. Let's see what we got here. Carr Bronze asks about quantum biology and expresses some skepticism, saying, I smell something funny, but with a smiley face. And no, quantum biology is a real serious and significant field. Mostly we think about quantum mechanics as being confined to individual atoms and molecules and things that are pretty small. But remarkably, scientists have found that there are certain quantum processes that take place in certain biological systems that have a macroscopic manifestation. I don't remember the details. We did a program on this in the World Science Festival. So if you're interested, just search World Science Festival quantum biology. But there are certain navigation systems in birds, I believe, in which scientists have traced the bird's ability to navigate on certain trajectories to certain quantum interactions between molecules in their brain and, say, the magnetic field of the Earth or things of that sort. So quantum biology is hugely exciting because it suggests that nature has found clever ways of leveraging some of the spectacular qualities of quantum physics into adaptive processes, adaptive behaviors. And at first sight, you say, well, why wouldn't nature do that? Quantum physics is real. Quantum physics affects how particles behave. And if a species comes along and by chance finds a means of tapping into those quantum processes more directly than we would have thought based upon, everyday experience with macroscopic things in the world around us. And if there really was adaptive value to it, then that species would have a better chance of having progeny and passing on to the next generation that very same ability to leverage quantum physics. So I don't think it smells funny at all. It smells kind of sweet and exciting. So from that perspective, it really is an exciting development to see quantum physics manifest in biological systems. Okay, what do we have here? Back to this feed here. Um, so UFlow says, Professor Greene, my name is Eugene, and here's my question. Can a clock be defined in a different way than a cyclical motion device? Atomic clocks, of course, are a cyclical motion device. And I'm always reluctant to say no, because there's always some clever thing that you can come along with. But it's hard for me to fully understand what a clock would be if in some way, shape, or form it wasn't relying on some kind of cyclical process. Because what we do to talk about the passage of time is we count the number of processes that go by between the beginning, the start of the event, and the end of the event. So we want a cyclical process, and we want it to be a stable cyclical process, so we can say, hey, it took 10 of those processes for so and so to drink that glass of water, or it took 59 of those cyclical processes for so and so to solve that math problem. Now, we often call those cyclical processes by seconds if we tune them in the right way. But it's hard for me to really understand what we would mean by the passage of time in terms of a quantitative measure if we didn't have some kind of cyclical process that was stable, so we could depend upon the cycles being identical, thereby lasting the same duration. So look, no doubt there's something that someone's going to come back to me on with that, but it's pretty profoundly woven into our thinking about time that we measure it with a device that has some cyclical process embedded within it. Okay. Okay, what else do we have here? Damodar Prasad S asks, is there a possibility for maths to be different in a multiverse if it exists? And sure, look, it depends on how you interpret mathematics. But actually, based on either interpretation, there is a version of your question that I would answer in the affirmative. So one way of interpreting your question is this: math, to some, is nothing but a language. It's a human invented language, just like English, just like Hindi, just like Swedish, whatever. These are all just languages that emerged by virtue of the human brain finding it useful to codify certain patterns. In natural language, the patterns that we codify are the typical things that we encounter in day-to-day life. In mathematics, the kinds of things that we quantify are more specific to particular processes that happen in the world. You bring two coconuts to your friend, someone else has one coconut, you put them together, you got three coconuts. There's a pattern there. And of course, we take those patterns as the brain matures and refines and describe ever more esoteric patterns, less and less available to everyday experience. But if you believe, as some do, that whether it's natural language or mathematics, it is simply a human invented construct, language, then of course, if there's a multiverse, it's possible that other members in other universes will have different mathematics. In fact, you don't have to go to a multiverse. It could be on other planets. Forget about the multiverse. On other planets, those living systems, they may have codified patterns in a different way. Or they may have found that the kinds of patterns that we find to be useful, the seasonal motion of the planets around the sun helps us know when to plant crops. If on that other world, maybe they live beneath the surface, they don't see the sun or a star. The notion of orbiting and orbital periods just has no pull, no value in their culture. The mathematics that they come up with may be quite different from the mathematics that we come up with. Maybe it's not even mathematics at all. Maybe it's a whole different kind of way of engaging with the world, and mathematics may not be anything that they've ever invented or paid attention to. Now, to contrast that, there are some people who think that mathematics is not invented. It's not a language. Mathematics is just truly stitched within the fibers of reality. And we, physical beings, are nothing but an incarnation of the underlying mathematical equations. That goes even further than anything that I really feel comfortable espousing. I'm not ready to say that math is so fundamental that any mathematical equation is relevant to the physical world. There are some who do. If you want to read about that, my friend Max Tegmark has a whole book on that. I think it goes a little too far for my taste. But if that were the case, then you might say, could other places have different mathematics? Well, they could have found different mathematics than we have found, but it's all part of one grand collection of ideas that we call mathematics. And we may have found one little island of that territory of math. Others may find other islands, but we would all be part of the same overarching fundamental structure, the mathematical reality that this perspective puts forward. So, two views each come to the conclusion that when we talk to the aliens, their math may be different from ours. Every reason to suspect that, in fact, it might be. Siavesh Sepantaman asks, how big is the unobservable universe? Well, good. The observable universe has a finite size. It's simply how far away objects can now be, and yet their light would have had time, say, since the Big Bang, to have traversed our separation and reach our telescopes or reach our eyes. And that number is about 45 billion light years in each and every direction. Beyond that is the unobservable, or the yet to be observed, depending on how the universe expands, universe. How far does the unobserved part of the universe go on? And the answer is, we don't know. It could go on forever. It could be infinite. Space might go on infinitely far, which is so easy to say and so difficult to really understand. Infinitely far. It never stops. Like, where did that come from? Who provided that amount of real estate? I mean, these kinds of questions come to mind because we live in a finite environment. Everything we encounter is finite. It's so hard to wrap your mind around something that is truly infinite. And who knows, maybe it's not truly infinite. It's a possibility, but nobody knows for sure. It could be that you travel out into space sufficiently far and you hit a wall. Maybe there really is an end out there, and that's not so crazy. There's a version of string theory in which you imagine the extra dimensions have a particular shape. And one shape that people have discussed amounts to having two brick walls on either ends of this universe. They might say, what's on the other side? Empty space? No, nothing. No reality is on the other side. It's hard to picture. Everything that has a border, right? I mean, this box, my AirPods, this box, it has a border. And outside the border, there's more space. But imagine that the border of the universe is the end of reality, not emptiness, not space that's yet to be inhabited, nothing beyond the end. That's a possibility too. Or it could be that space wraps in on itself, right? I don't have my basketball here any longer, but it could be that space is curved. You go out in space in one direction, you go far enough, and ultimately, without even turning around, you wind up returning to your starting point from behind your initial location. That's what happens on planet Earth. If I walk out in that direction, I go far enough, I will circle around, I'll circumnavigate the Earth. You perhaps can circumnavigate the universe if it has the right shape, which would mean that it's finite, it does not go on forever, and yet there's no wall that you encounter. It's simply the shape allows it to have the property of finiteness without an edge, without a boundary. So, yeah, it's a great question. It's a tough one. That's the current state of the art understanding. Christopher asked, Dr. Greene, which is your favorite? My favorite what, Christopher? You must have been referring to something I said at that moment, but I have no idea. So, Chris, if you want to chime back in, I'd be happy to tell you what my favorite is. But without any noun there, it's hard for me to answer. Ludwig von Beethoven is back. So good to see you again, Ludwig von Beethoven. It's the name that always sticks with me because I am a great fan of the Ludwig von Beethoven. But anyone who has his name, I assume, is a fan as well. I see. Confirmed. The World Science Festival is sponsored by Apple. We're not sponsored by Apple. I'd be happy if we were sponsored by Apple. I would happily take their support to create all sorts of cool content. So if you guys want to lobby Apple to support us, I'd be all too happy. But when I pick up any of my gear, it is simply because it is around me. There is zero product placement. There is zero monetization happening on any of the stuff that we are doing. This is all just to bring these ideas out there. No motivation beyond that. Okay. I've been told by Siavash that I butchered the name. Sorry. And there's no way, maybe you could spell it out phonetically for me next time and do my best. Okay, so we have Rye Guy asked, Dr. Greene, can you go into more about the difference between the 50% chance of spin with quantum entanglement, right, versus the 55% theorized by Einstein? Where did the 5% go? Good question, good question. So remember how this went. Actually, I'm gonna have to take a sip of water. This question is good. It's gonna take me a moment to answer. So remember Einstein's perspective. He says, come on, quantum mechanics people. Can you really believe that if you have two widely separated objects, each in a fuzzy statistical mixture of going up and down, that if you measure one, that it can have an impact on the other, arbitrarily far apart, arbitrarily distant from the first? He says, come on, you can't possibly believe that. And he says, I've got a better way of explaining what's really going on here. Einstein says, look, your quantum math says this particle is in a fuzzy mixture, 50% up, 50% down, but that's not what's really going on. That's merely a limitation of the quantum mathematics to describe the true reality. If you measure that particle and you find it up, it always was up. The math might have said it was doing this, but it wasn't really doing that at all. It's a limitation of your knowledge of reality. It was up all the time. When you measured it, you simply found what was already there. Similarly, if this one you measure it and you find it down, it was always down. So there's no spooky action, because when you measure this one and find it up, it was up. When you measure this one, you find it down, it was down from the get-go. Always we're in this complementary pair of up and down. John Bell comes along and says, well, Einstein, he couldn't talk to Einstein directly. By this point, Einstein had passed away. But Bell, in essence, says, well, Einstein, that's an interesting suggestion that particles always have these definite features, even though quantum mechanics is saying that they don't. Is there a consequence of that? At first sight, people thought no. Remember, I think I mentioned that Wolfgang Pauli attributed the way of thinking about the world to being no better than trying to count angels dancing on the head of a pin. It's as if again, the example I used with you guys, I'll use it again. It's as if I say to you, hey guys, my hair color is actually in a fuzzy mixture of pink and blue when you're not looking, but when you look, it snaps to one definite gray or white, whatever the right description of my hair color may be. How can you ever test that was in a mixture without measuring? But everybody says once you measure, you find a definite result. So it seems like it's untestable. Now to your question about the 55% Rye guy or Re guy. John Bell shows that if you are measuring the particles in a more clever way, not just along one spin axis, but along 3 spin axes, he finds that there is a measurable consequence to Einstein's perspective that the particles have a definite spin when you're not actually even measuring them. He finds that these detectors, if you do random measurements of the particles on a great many runs of the experiment, they should disagree. The particles should be up and down at least 55% of the time. That's a consequence of Einstein's vision that there's no spooky action and that therefore particles have definite features. That's testable. You do the experiment and you don't get Einstein's prediction. You find 50% of the time they are found to be in these oppositely oriented pairs. So where did the 5% go? It was never there. Einstein's prediction was wrong. Einstein didn't even know it made a prediction. It took John Bell to figure that out. But in essence, Einstein's vision of the world, no spookiness and therefore definite features, is ruled out. What does that mean? Well, Einstein's vision, no spookiness, therefore definite features, that's wrong. Therefore, there is spookiness. There can be spookiness and definite features, but there has to be long-range connection in this way of thinking about things. That's the answer. The 5% was an incorrect prediction. The 55%, therefore, was an incorrect prediction. 50% is the right prediction, and it's the quantum mechanical prediction. All right, I hope that clarifies there. I got to ask again if I didn't convince you of that. So what else do we have? Should I look maybe on a Twitter thingy? What do we have over here? Hement Shriek asks, hello, sir. Can you help us imagine non-Euclidean geometry of space-time? Very hard. I can help you understand non-Euclidean geometry of space, but I know that's not what you're asking. Non-Euclidean geometry of space is just non-flat surfaces. That's the two-dimensional version, and the surface of a basketball is a really good example of a non-Euclidean in the sense of non-flat surface. But to bring time into the story, it's harder to picture mentally. You know, the diagnostic that I gave in the last year daily equation is, I wonder if I can even bring my iPad up just to remind you of the diagnostic. I'm going to try to do this. I hope I don't cut everybody off. So did that work? Am I on this thing here? I'm trying to share my screen with you guys. Let's see if this works. If it doesn't work, then I'll go back to just describing things in words, but I think this is going to work. And let me bring up a notability thingy here. So hopefully that's working with us right now. And you may recall that I gave you a diagnostic for when a shape is curved. And the diagnostic is you take a vector at some location in that space. And what you do is you move that vector around. So I'm going to do that here. I'm going to take a copy of this guy, put him over here, paste it, and now I'm going to move it. And notice as I move this vector around on the plane, regardless of what path I follow, when I get back to my starting point, the new vector is pointing in exactly the same direction as the original vector. On a curved surface like a basketball, in fact, I used a basketball last time when I was describing it, that will not be the case. You don't return to your starting point. The vector instead points in a different direction. Why do I bring that up? I bring that up because imagine you're in space-time. And in space-time, you can carry various things around. You can, for instance, carry around a clock. And as you carry around this clock, the question is when you return to your starting point, will the reading on your clock agree with the clock that stayed at your starting location? And the answer to that in general for curved space-time will be no. As you parallel transport it around in the language of the field, it does not return to its original configuration. So curvature for a basketball, that makes sense. Curvature for space-time, harder to envision, but it's the same kind of diagnostic tool. Fundamentally, it's the same mathematics. All right. Eric W. asks, you mentioned working all the time, no interesting hobbies. Well, over time, I've sort of found that my hobbies have inserted themselves in my work in a sense. You know, I'm a great fan. I love music. I love the arts. My dad was a vocal coach, a bass player, a musician, a composer. And so I grew up in a household that was filled with that kind of an artistic environment. And so for a good fraction of my life, that was sort of a hobby-esque part of what I do. But you may have seen, I've mentioned it before, that with World Science Festival, we've been blending art and science. In particular, projects that I've been involved with have blended music, blended stage, blended physics, all in sort of one interesting unified package. Another project that we're working on right now is the story I wrote about a boy going to the edge of a black hole, Icarus at the Edge of Time, which we collaborated with the composer Philip Glass to create a live stage presentation. Where we have a sequel to that that will be coming out, as soon as the world gets back to normal, if that ever happens. So again, that's a blending of my own interest in music and stage presentation together with the bread and butter of my professional career, which is physics and calculations and things of that sort. So I'd say over time, the things that I do have become so enmeshed with one another that I don't even consider a distinction between what's a hobby and what I do. They've all kind of blended together into one whole. All right, what else do we have here? Jessel Vora 1 says, what's the biggest question facing physics in your opinion? Well, it partly depends on what kind of physics you're talking about. I, of course, come from the arena of fundamental physics, gravity, quantum mechanics, things of that sort. And in that domain, I would say the fundamental question facing us is, what is space and what is time? That may sound silly, right? We've been formulating our theories within a notion of space and time for centuries. Isaac Newton puts forward, space is the arena, time is that which allows us to measure that change has occurred, and the events of the universe take place within that rubric. Einstein comes along and realizes, well, it's more complicated, it's more subtle. Space and time can warp and curve. And in that way, they're participants in the cosmological unfolding. Space expands. Time elapses at different rates if you're near the edge of a black hole, if you're back here on Earth. But all of that, however insightful it is, doesn't tell us what space is, doesn't tell us what time is. We can measure these things with great precision, but we kind of don't know what they are. And progress has been made. There's work in string theory that suggests that space and time may themselves be made up of more fundamental constituents, and they may be constituents that are in some sense, threaded together, held together by the threads of quantum entanglement. These are very exciting ideas, but they're tentative. So, in answer to your question, I think the next big revolution will come when these ideas are not so tentative, when we have consensus on what space is and what time is, with the hope that once we understand things well, I mean, the pattern has always been you don't understand something, you work hard at it, you research it, you experiment, you bang on it with mathematical equations. You do understand it. Fantastic. Next step, you manipulate it, right? Quantum mechanics was just a collection of ideas that allowed us to better understand the hydrogen atom, the motion of electrons back in the 1920s. But now we regularly use quantum mechanics to build things. The devices of everyday life rely upon quantum mechanics. So the pattern is you don't understand something, you work hard, you do understand it. You work hard again, and now you can manipulate the thing that you began with. So if that pattern were to hold true with space and time, you don't really understand it. You work hard, you understand it better, Einstein, relativity, and so forth. But if we can go that next step and really fully understand it, and by that means be able to manipulate space and time the way we manipulate electrons with quantum mechanics, wow, what could that portend? What could that mean? What could that yield? The ability to willfully manipulate space and time. That's exciting. That's what the next generation of you young physics enthusiasts, you may enter that domain of being able to manipulate space and time at will. I hope I'm around when that development takes place. Nave Ball asks, hi, Professor, how does general relativity help in the formation of the GPS, global positioning system? Yeah, that takes us another example, right? I mean, I just mentioned how quantum mechanics allows you to manipulate electrons, and that allows for the whole modern electronics industry relying upon quantum mechanics. The GPS is an example where Einstein's general relativity has concrete applications. Why? Well, how does the GPS system work, right? So the GPS system, you have these satellites orbiting the Earth, and we have these devices that can communicate with the satellites. They can receive signals from the satellites. And if your device receives a signal, say from 3 of those satellites, and those signals are time stamped, so you know when those signals left the satellite, by virtue of the time difference of the arrival of those signals, you can calculate where you must be on planet Earth, because you can calculate your distance from each of the satellites, and that can uniquely delineate which point you are occupying on planet Earth. But critical to that is that the satellites are all completely synced up in terms of time, that they are registering 12 noon at the same 12 noon. And it must also be the case that your phone is ticking off time at a rate that allows it to stay in sync with the clocks on the satellite. But bear in mind, the satellites are farther away from planet Earth, experiencing less of a gravitational field. According to Einstein's general relativity, their clocks intrinsically are ticking off time at a faster rate. If you didn't take that general relativistic effect into account, then all the calculations that I just spoke about in terms of the time differences and triangulating your location would be completely off. They'd be wrong. The clocks on the satellite and the clocks on your iPhone would be so out of whack relative to one another that the GPS system would fail. So you have to include the general relativistic corrections in order that the GPS system works. And indeed, that's what is done. So it's a beautiful example where the general theory of relativity comes right into our pockets when we're carrying around a phone that has GPS sensitivity embedded in its technology. So, yeah, quite wonderful to see general relativity as an applied science in that particular way. Okay, let's see what we got going on here. Wow, it's already 4:20. Usually it's around 4 o'clock that I say I'm about to stop, and then I keep on going for another hour. But so Weirdo 2.7182818. Hello, Professor. What do you think? Oh no, where did it go? I touched this thing and it scrolls by so fast. Sorry, E, which I guess was the number that you had there. I've lost you, and I'm scrolling back to try to find your question. I can't find it. Oh no, there it is, way up there. Weirdo asks, hello, Professor. What do you think about pure mathematics? I'm in favor of pure mathematics. I support pure mathematics. I would vote for pure mathematics. I agree with the platform of pure mathematics. And what I mean by that is, people are motivated to do work by different considerations. When I was in college, I was thinking about doing pure math. And the reason I wound up not doing it is it sort of felt to me like the problems in pure math are the problems that we make up. We envision interesting questions like how many spheres can you pack in a particular shape? Or what is the density of prime numbers if you look at the number line? Or things of that sort, right? And they're interesting questions, but they are ultimately questions that we come up with. What I found more appealing about physics is that the mathematics that you do is trying to solve problems that you don't come up with, but rather that the universe comes up with. The universe presents us with gravity, we want to understand it. The universe presents us with electrons, we want to understand them. So somehow it felt to me that the math is being used to answer questions that are less arbitrary, questions that are part of how reality is constructed. So that motivates me more than the questions of pure mathematics. But oftentimes, the questions of pure mathematics in time have proven to be relevant to physics. Einstein borrowed the pure mathematical insights of Gauss and Riemann and others in order to understand curved surfaces. But the surface that Einstein had in mind was space time, the manifold called space time. So it's really exciting when the pure mathematics unexpectedly has an impact on physics, but you have to do whatever fires you up. And pure mathematicians are fired up more by questions of their own making within the universe, if you will, of math, as opposed to the universe of space, time, and stuff. Okay. Seth Catalano asks, what is a good geometric intuition for what the Einstein tensor measures? As the Riemann tensor measures the acceleration of the separation of two paths, and the Ricci tensor measures the change in volume. So here's how I think a good way of measuring, of thinking about the Riemann tensor. Maybe I'm gonna go back over here. So starting a broadcast. Let me go to my iPad. Can it work? Yes, it does. Okay. So when you think about the Riemann tensor, so if you have R, alpha, beta, gamma, delta, the question is, what is this thing measuring? And what I like to think about this measuring is it's a measure of what I have over here. It's a measure of the degree of variation. So let me choose a different color here. So imagine you've got a shape like this, and you take some tangent vector over here, give it a different color. Come on, hot pink is a nice one. Let's say you have a tangent vector over here, and you slide it around to, let's say you slide it around over to this location. Boy, I'm having a little bit of trouble here. Hit a little bit of lag. There we go. And that's sort of path one motion. But let's say you take that same vector and you parallel transport it around the loop in the other direction, and let's say it takes you over here. And in general, as I was saying before, on a curved surface, the vectors that you get by that parallel motion will not agree. What does the Riemann tensor do? The Riemann tensor measures the difference in the direction that those two vectors point. And that's really what it does. And as we'll see when we come back to your daily equation next week, I may derive it in some detail, but you'll see quite directly that the Riemann tensor is nothing but the gadget that captures the difference between two vectors parallel transported opposite directions around a loop, and that is the diagnostic for the surface being curved, and that is indeed what the Riemann tensor measures. Okay, so what do we got? Do I have my iPad down? I think I do. Tell me if I don't. AG writes, AG until the end of time. Oh, nice. So you have the title of my book. You wrote about the infinitesimal odds of particles arranging into orderly low entropic states. Billions of people interact with reality daily, so why haven't we heard or seen said phenomenon? And yeah, you're right. You know, I'm fond of emphasizing that the second law of thermodynamics talks about the increase of entropy, but it's not a law. Really, listen to me. The second law of thermodynamics is not a law in the usual way that Newton's law is a law, or Einstein's equations are a lawful description of how a physical system evolves. The second law of thermodynamics speaks to an overwhelming likelihood of what will happen. And the overwhelming likelihood is that entropy will increase. Common examples: if I were to drop my iPhone, I'm not, oh, Apple product again. You're going to accuse me of product placement, so let me take something else. So if I was to take this candle, all right, it's a glass jar. If I was to drop this, we know it will smash on the floor. That's going from order to disorder. The reverse process is possible, where, as the questioner asks, the shards of glass on the floor, in principle, they can jump off the floor, reassemble into this pristine glass candle. The question is, why haven't we ever seen that? And it's a very straightforward answer. If you look at the number of events that all the people on planet Earth, right? So I don't know how many people have lived since the beginning of our species. I'm going to make a wild guess. Let's call it, I don't know, 50 billion people, 100 billion, I don't know. So there's some number. You can look it up. You tell me. Think about the number of seconds. Call an event sort of it takes 1 second to see an event. Think about the number of seconds that have elapsed since the beginning of our species. That is the number of seconds that people have lived. That's a number. I don't know what that number is going to be. I don't know. Let me call it, I don't know. Let's call it 10 to the 20. You know, I don't care. Something like that. If you compare that number to the odds of the glass shards jumping off the floor, because the floorboards and the molecules of air in the room all reverse their motion in such a way that they hit the floorboards, and the floorboards jiggle in such a way that they kick the glass shards off my floor to reassemble into this glass. The odds of that is spectacularly less than 10 to the minus 20. It's 10 to a huge number. And therefore, it is completely unsurprising that no one has ever seen that process happen. And no one has ever seen an egg unsmashed. No one has ever seen a candle unburn. No one has ever seen a person resurrect or, say, evolve from an elderly physical form to a young physical form. It's not that these processes can't happen. They are allowed by the laws of physics. It's just that the odds of them happening is not just small, it's spectacularly smaller than the number of events that every human being who's ever lived has ever encountered. And that's why it makes perfect sense that no one in a replicable manner has ever claimed that they have seen an entropically decreasing process to happen. Okay, if that doesn't satisfy you, feel free to ask again, but that is what it is. Let's see what we got. Mr. Castle asks, going to black holes, can photons be trapped in stable orbits outside of a black hole? Photons can be trapped in orbits around a black hole. So maybe we'll do this if you want. I'm going to talk about the black hole solution to Einstein's field equations of general relativity. And once you have the solution, you understand the geometry outside of a black hole. Once you understand the geometry, the warps and curves in the vicinity of a black hole, you can calculate how things will move. How do you calculate that? Objects want to move along the shortest possible trajectory. They're called geodesics. In order to figure out the shortest possible trajectory, you need to know the geometry. Once you know the geometry, you've got everything that you need in order to figure out trajectories. And indeed, you can find trajectories that light will travel. Light itself will go into orbit around a black hole, but it's not a stable orbit. If you were to perturb that orbit a little bit, photon goes one way or the other, away from the black hole or toward the black hole. So you can have photon orbits. Absolutely. That's pretty cool. That's pretty surprising in its own right. Brad Dibble asks, Dr. Greene, I love baseball and physics. Great. Does the Louisville Slugger in your room have any significance? Do I have that slugger in here? Maybe it's, yeah. Oh, actually, it is. I see it in the back corner over there. Does it have any significance? Well, I actually once did a physics video with the New York Mets, baseball team, New York Mets. I went to them and I described how the various things like the Magnus force are responsible for why a baseball curves when a pitcher throws it appropriately. I described how a baseball bat has a frequency response function that determines where the sweet spot on the bat will be when a batter is swinging that bat. So I too love baseball, mostly because my son loves it and he sort of wrote me back into the sport after I hadn't really thought about it for many decades. But the reason why I have the Louisville Slugger in my room here is a little less erudite than any of those descriptions might suggest. And by the way, you can find those Mets videos, those baseball Mets videos online. Maybe it's even on the World Science Festival website. I don't know. But the reason I have the Louisville Slugger here is that I am in a little writer's cabin. You can sort of see I'm, by a barn, somewhat in the woods. I don't know, about 300 feet from the main house where my family is and where I sleep. I sometimes come out here at night. It's kind of dark, pitch dark, and I'm always somewhat concerned that a coyote or a bear might want to have a conversation en route from my house to this cabin. And so, to dissuade certain kinds of conversations with those wild animals that I would prefer not to have, I bring the bat with me. No doubt, in a wrestling match with a coyote or a bear, I think I'd lose even with the baseball bat, but psychologically, it makes me feel a little more confident as I cross in the darkness. That is the only reason the baseball bat is here. Let's see. Robert Taylor asks, do we humans give meaning to the universe? And if not, what is the meaning of it all? What is the meaning of it all? Robert Taylor asks. And yeah, as the book I wrote recently, Until the End of Time, a little bit different from my previous books in that it takes up questions like that. What is the meaning of it all? And look, my view on this is the following. Fundamentally, there is no meaning built into the architecture of the world. There is no fundamental notion of meaning, to use another metaphor, that's stitched into the fabric of reality. At rock bottom, as I said before, I believe, and I think the evidence strongly supports the perspective, but it doesn't prove it, that reality is nothing but stuff, fundamental ingredients governed by fundamental laws that we may or may not currently have at our disposal. And that's it. So from that perspective, you can't look to physics to provide any notion of meaning or purpose. Meaning or purpose are concepts that really only come into existence when certain sophisticated, refined collections of particles are able to form. And they form via the process of natural selection. That's why we are here. The fundamental laws are supporting a process that Darwin was able to identify, in which molecules can become ever better adapted to their environment, ultimately allowing complex structures like life and like conscious beings to exist. And therefore, when we ask ourselves about meaning and purpose of it all, we are asking a question that couldn't even be asked until self reflective conscious beings emerged. And therefore, what kind of answer should we search for? Should we search for an answer in the fundamental equations? No. Fundamental equations don't know about this notion of meaning and purpose. Where should we search for the answer? We have to search within ourselves, because we are the conduit by which this question is able to be asked. And so ultimately, it's a very personal question. This way of thinking about things frees us up, at least from my perspective, to stop looking for some meaning out there in the world. And each of us is charged with the task of manufacturing our own meaning. And by the word manufacture, I don't mean to denigrate in any way, shape, or form the concept of value or purpose or meaning. Not at all. I think that the fact that we manufacture it makes it exquisite, aggrandizes it, because unlike other approaches that may look out to some being or look out to something in the world to bestow meaning upon us, that version, we're just wearing someone else's notion of value and person, some external forces conception of value and purpose. It is so much more noble to come up with our own value, our own purpose. And that's something that Robert Taylor, you need to, I knew, everyone needs to do it on their own. Now, look, from my perspective, understanding physics, understanding the universe, that's part of where my value and purpose comes into the story. Having these conversations, spreading insight that physics has revealed, that gives me a sense of value and purpose as well. Revealing some fundamental quality of reality, however minor it might be. On those occasions, I have felt enhanced value and purpose through that achievement. These are the things that we use. And of course, my family, right? My wife, my kids, that is a source of great value and purpose as well. So you won't find it written into the stars. You won't find it written into the molecules. You'll find it if you allow yourself the freedom to make it up. Find what gives you that sense of purpose and value. And that is a highly personal, highly subjective, but deeply exquisite way of addressing the question of meaning. I'd be interested if you guys feel differently than that. No doubt some of you have a radically different perspective. Put it in the comments. I'd be more than happy to hear different views. All right, carrying on with the more physics-oriented questions that I see coming first. Psi asks, PSI, I guess, or psi, the Greek letter psi. My question is to Dr. Greene. Yes, they're all coming to me unfiltered. Will matter decay in the future? Will protons decay? And if they will, does that mean that time stops? Will time come to an end? So we do not know if protons will decay. We believe that every other particle, except the lightest ones like electrons, neutrinos, and photons, the belief is that they are likely stable. But conglomerates, right? A proton is 3 quarks. The conglomerates, we believe, will all fall apart, but we don't know that for sure. Neutrons certainly fall apart. Short period of time. Hold a neutron in your hand, a bunch of them in your hand after, a short period of time, 10 minutes, half of them will have disintegrated. Protons, we have tested, we've looked at large, huge tanks of water and other fluids, looking for one measly proton to fall apart. We've never measured it. Our mathematics suggests that protons will fall apart. Different theories give different time scales. 10 to the 35, 10 to the 38 years is the half-life for a proton, but as yet we don't know. But I would say that most physicists anticipate that protons are not forever, that they will also fall apart. Now, the question is, when they all do fall apart, does that mean time stops? And people use that language. When all complex matter has disintegrated, all stars have disintegrated into a spray of particles, is it all gone in the sense that time doesn't tick forward? Well, time may end in the sense that there won't be any meaningful notion of change. If all you've got are particles floating through the void, then it kind of doesn't matter whether one particle's here and one particle's there or one particle's moved. So in that sense, there won't be anything happening. And if time is a measure of change and change has to rely on things happening, then yeah, in a sense, in a poetic sense, time will have stopped. But particles will still be moving, and they're moving through time. And so, in that sense, time may go on forever, even though there won't be anything interesting happening. Now, again, if you're interested in this in more detail, chapter 10 of my book, Until the End of Time, takes this on and notes that in the very far future, if you wait like 10 to the 68 years, then even these particles floating through the void can, on occasion, randomly coalesce into interesting structures, structures that, in fact, may be able to think, to cogitate. That's weird. That's curious. Wait 10 to the 68 years, and a human brain, may spontaneously form out there in the void. Sounds nutty, maybe nutty. We generally use this as a diagnostic tool to try to modify our theories to not allow this process to happen. These are called Boltzmann brains after Ludwig Boltzmann. So if you're interested in the idea of Boltzmann brains, again, you can read chapter 10 of Until the End of Time. But barring those kind of rare occurrences that may happen in the far future, the absence of change in some poetic sense can be interpreted as the absence of time. So yes, in short to that question. Campus cryptoid. I'm reading Until the End of Time, and almost every footnote redirects to chapter 10. That's not quite true. It's not that every footnote redirects to chapter 10, but chapter 10 is where it kind of all comes together, where I lay out the very, very far future. And in a book that's called Until the End of Time, the chapter that takes you toward the end of time is going to be a pretty vital one. And that's why chapter 10 has the prominence that it does. Dalman Ketterpal asked, does a spring gain mass when it's compressed? Does potential energy convert to mass? And the answer is heck yeah. So if you have a spring and you compress it, right, and you were to weigh that spring on an incredibly precise scale and compare the reading when the spring is in its relaxed ordinary state, the reading on the scale will be bigger when the spring is compressed. The energy that you push into it, as you say, it's this potential energy, but Einstein's E equals mc squared takes into account all energy. It's really saying that energy and mass are different labels for the same kind of thing. And so by putting more energy in, you've put more mass in, and that mass would be reflected on the reading of a scale. Similarly, as I'm fond of using as an example, if I have a flashlight and I put the flashlight on a spectacularly sensitive scale, and I turn the flashlight on, or the torch, as some of you like to use the language, as the light races away from the flashlight, it takes away energy, right? Light has energy. It's taking away energy from the flashlight. Taking away energy means you're taking away mass, which means the reading on this fantastically sensitive scale will go down if you keep the button in the on position for the flashlight. T-Bald asked, dear Professor Greene, greetings from, God, it ran away. don't do that. I'm going to try to find that question. I should never touch the pad here when I'm in the middle of asking a question. That's why this happens to me. I'm trying to find your question. I'm scrolling up. Maybe ask it again. I can't see it, unfortunately. So I'm going to move on to another question. Sorry about that, T-Balt. Mr. Castle asks, "Dear sir, are there equations that you don't understand?" It depends what you mean by understand. I feel like I understand the key equations of modern physics in the sense that I know where they came from. I know what they're trying to tell us. But do I understand them deeply, intuitively in my bones? Some of them, yes. Some of them, no. I often find that I have to go back and rethink things, especially when I'm teaching a subject. Even if I think I understand the subject inside out, I'll come upon some equation and say, well, wait a second. Wait, what is that really telling me? And where does that really come from? And what's the chain of reasoning that gets me to that equation? I find that I have to go back and refresh myself in order to keep the chain of reasoning really sharp inside my brain. So you should never be, what's the word? You should never be, what's the word? It's not disgruntled, distressed. It's a very basic word. You should never feel bad. Tell me what word I'm looking for. If you sort of find that you have to go back and relearn something from the past, I've got to do it all the time. So in that sense, I have to refresh my understanding. But there certainly are fields of mathematics that I've given up on. Somebody asked earlier about math that I was surprised had a role in physics, and I described algebraic geometry as an example of a field that unexpectedly I had to learn parts of it to do certain research in string theory. But there are other parts of algebraic geometry. In the book of Joe Harris has a beautiful book on algebraic geometry, and there are chapters in that book that defeated me. I wanted to understand those chapters, and I never felt like I really did. And there are other chapters that I didn't even bother to try to read. So in that sense, there are equations in pure mathematics that I feel stretched my brain to the limit. And could I have learned them if I really, really, really tried? Maybe. But it was the getting to a point in certain of those undertakings that I felt like every time I went further in understanding part of the subject, another part of it would sort of disappear. It was almost like a conservation of the amount of brain space that my brain was willing to allow the equations of algebraic geometry to fully inhabit. So, yes, there are definitely things that I've tried to understand and felt like I didn't fully master or felt like I had reached my limit. Okay. Ludwig von Beethoven asks, "Will you write an autobiography someday in the distant future? Great source of inspiration to me and many others. We'd all be honored to be enriched by your life experience." That's so sweet of you. I appreciate that, Ludwig von Beethoven. I don't know. I'm not sure. It's never really occurred to me. But in my latest book, there is much more personal reflection than I've had in any previous book. And some people have asked me why, not in a accusatory way, but they were just curious about my own thought process that led me to include more personal reflections in Until the End of Time. Let me tell you why. The point of the book Until the End of Time is that there's not one way of understanding reality. We physicists focus on the fundamental particles and the fundamental laws, and that's what we're really talking about here today. But to have a full account of the world as experienced by a human being, you need to layer various other accounts into that story. You need to layer the account that the chemist gives, that the biologist gives, but you can't stop there. You need to give the account that the philosopher gives, or the neuroscientist gives, or the artist gives, or the theologian gives. And all of these accounts serve to enrich your understanding of what life and what reality, what the world is all about. And so it felt to me that it would really be unfortunate in a book that's talking about these layered account, these layered stories, to not include the only human story that I have direct access to, which is my own. So at various moments, you will see that I do layer in personal experience and personal reflection as part of that nested account so that the narrative can be as rich as possible. But whether I'll go further one day and actually write an autobiography, I don't know. I don't know. We'll see. We'll see how things progress. Okay. Alpha Omega asks, if all information is stored in quantum entanglement, doesn't that mean eternal life actually happens? And I would say no, not at all. So you can have a system whose information content is fully stored in the quantum state of that system. And if you then conclude, or at least hypothesize, and it seems to be well bolstered by our understanding of physics, that information is not destroyed, that the information is always there. At best, what I'd be willing to say is that in principle, all the information contained in a given human brain, that information can in principle be recreated by infinitely precise measurements that take place after that being may have expired. But at best, you can imagine using that information to recreate the original living system. It's not that the living system itself is eternal. You know, it's hard to define what you actually mean by death. I was actually reading a book recently by a philosopher who is, struggling to give a precise definition of what it means when we die. But I'm pretty satisfied with the straightforward definition. When this physical structure called Brian Greene, when it no longer functions, when it no longer carries out the basic processes that we define as living, when it no longer breathes or eats or thinks, that's to me when it has died. And when it dies, sure, in principle, the information content and all the constituents and their various interrelationships could in principle be recorded and could in principle be recreated, but still I'd be dead. There could be a recreation of me, perhaps. Maybe we'll get to that point. Maybe, in the sci-fi books, we imagine uploading ourselves into a different physical structure. Will that ever happen? I have no idea. But even if it does happen, it's not to say that this living system that originated the thoughts and feelings and emotions and memories won't have died. It will have died. We'll simply have found a way of capturing its patterns and allowing those patterns either to be recreated or to persist. That's different from saying that the living system itself is eternal. Ah, yes, Joe Harris is the other author, as Evie notes to me on that book. So Griffiths and Harris. Yes, it's Griffiths and Harris. That's what it is. Exactly right. Thank you. Um, let's see what else we have. Somebody is directing me to a question on Twitter, but I don't know what question that is. Sorry. Let's see. So I like that. I am asked, what is the difference between gravity and quantum gravity, and why are we after the latter? Why are we after quantum gravity? So it's quite straightforward. I am, and the answer is simply this. So in the early days of trying to understand reality, Isaac Newton gave us the universal law of gravity that perhaps you know about, F equals G m1 m2 over r squared. We call that a classical formula because it does not take into account the realizations that we acquired in the 1920s and 1930s that the world's not actually governed by the classical laws of Newton. There's another class of laws, the quantum laws. And we've been very good at applying those quantum laws in situations of individual particles, collections of particles, molecules, and atoms, and so forth. The equation that we make use of is called Schrodinger's equation. Now, although we understand gravity in the macroscopic way that it manifests itself a la Newton in F equals G m1 m2 over r squared, there are situations in which Newton, gravity, and quantum, small things, need to be blended together. So a quantum theory of gravity is a theory of gravity that will work not just for stars and planets, but will work for individual particles like electrons and quarks and protons. And moreover, it will work in any situation where a quantum description of the ingredients is necessary. So a quantum theory of gravity blends the rules of quantum mechanics with the rules of gravity in a manner that allows us to apply the gravitational force in any circumstance, not just planets and galaxies when things are big, but also to the realm of small. So being even more precise, Einstein gave us a more refined classical theory of gravity. The general theory of relativity is a classical theory. It doesn't speak to quantum physics. So our goal has been to blend Einstein's theory of gravity, the theory, if you will, of big things, with quantum mechanics, our theory of small things, so that we have one unified description that works for the small, works for the big, works for everything in between. Right now, we have a fractured description. We use quantum mechanics for the small, Newton or general relativity for the big, depending on the circumstance. We don't want two theories. There's one universe. There should be one theory that puts it all together. That's the goal of a quantum theory of gravity. All right, so let's see what we have. Sir, in your book, Fabric of the Cosmos, you have mentioned that space and time are moving equal to the speed of light. Please explain to me as one of your readers. So I think what Safi K. Raza is referring to, Safi K. Raza is referring to, is that any individual can be thought of as though they are moving through space-time at the speed of light. What do I mean by that? Well, for light, it's obvious. Light just moves at the speed of light. But what about me right here? Imagine that from my frame of reference, I'm not moving through space at all. Am I executing some motion? And the answer is I am. I'm moving through time, right? My clock is ticking off second after second after second. So if we don't just think about motion through space, but also think about motion through time, then I'm moving right now. I'm moving through time. At what speed am I moving through time? And it turns out that one way of interpreting Einstein's special relativity is that I'm moving through time at the speed of light. And in fact, any motion at all, when thought about not just as motion through space, but as motion through space-time, has a speed equal to the speed of light. Why is that useful? That's useful for the following reason. If I now get up and start to move through space, according to Einstein, Einstein doesn't say it this way. This is sort of my interpretation. There are others who say this too, but I kind of saw myself writing this interpretation down the first time in The Elegant Universe it was, but whatever, who cares about credit or anything like that? But when I get up and start to move through space, I divert some of my previous motion through time into that motion through space, and therefore my passage through time, my motion through time slows down. When I get up to move through space, it affects my passage through time. That's why if I look at you getting up and walking, and I look at your wristwatch, I will see your watch ticking off time slowly. Why? The previous motion that you had was all through time. You got up and you have a fixed amount of it. You're moving through at a fixed speed. And therefore, if you get up, you divert some of that fixed speed from the previous motion through time into your motion through space. And therefore, your motion through time slows. Therefore, your clock ticks off time more slowly. That's one way of thinking about why it is that time slows down for an object that you are looking at in motion. Why does it slow down? Because there's a fixed amount of motion through space-time, and it is diverting some of that motion into motion through space. Therefore, the previous motion through time must give up some of its speed. It must slow down. Clocks must tick at a slower rate. That, to me, is the most beautiful, most intuitive understanding of why it is that when an object moves, time slows down. Pericles Mello asks, do you have a video on the double slit experiment that shows that an observer behind the slit collapses the wave function and the pattern of superposition on the screen? I don't have a video of it, but I'm wondering, Pericles Mello, why you're asking for one, because your description is pretty darn good, right? In your mind's eye, you can picture no observer. You got the particles going through the two slits. You get the interference pattern, light, dark, light, dark, light, dark on the screen. If you then modify the experiment by putting an observer on the other side of the barrier who measures the slit through which a particle goes, that interaction changes the experiment. Has it changed it? The particles will no longer land in this nice light, dark spread. Instead, they will fan out and just give us an overall smear on that back screen. No interference pattern at all. So your description captures it right. So I think your mental image is just as good as any video image that I could give you. Amanda says, time has to compromise for space. Yeah, that's right. Here I am. My watch is ticking off time. All right. I get up and I start to walk, and you will see time compromising for space. Time is giving up some of its fixed light speed motion so that some of that motion can be diverted into my motion through space. That's it. That's really what Einstein found in the special theory of relativity. Totally intuitive when you think about it that way, however strange the implication may be. Okay. Oh, okay. T-Bolt has re-asked the question. Thank you. And I'm not going to touch, so I'll read it. Dear Professor Greene, I recently became a big fan of yours. Exclamation point. Thank you. My question is, or was, why are past, present, and future an illusion? Thank you very much. So T-Bolt, you're referring to a quote of Einstein's, a famous quote. It was a quote that Einstein wrote to the widow of his friend, Michele Besso. And what Einstein said to Besso's widow was, the fact that he has departed the world a little before me has no meaning, because the distinction between past, present, and future is only an illusion, however persistent. That's the translation that I prefer of that quote. I think it's a quite beautiful, quite poetic quote. How do you interpret that physically? What was Einstein thinking? Well, look, he was writing to the widow of a friend, so trying to overlay a precise interpretation might seem a little crass, but let me give you the interpretation that I think works best. So, in the special theory of relativity, we learn that our clocks tick off time at different rates if we are moving relative to each other. What does that mean? That means that what you consider to be right now may not be what I consider to be right now. Your now may be what I consider past. Your now may be what I consider future. And similarly, for your consideration of my notion of now, which means if you consider everybody's perspective, imagine that there are perspectives all throughout the cosmos, even hypothetical perspectives, all moving relative to one another and so forth. And if you take into account every individual's notion of now, then you basically will span all moments of time. Moments that I consider to be way in the past, someone way out there will say, no, no, that happened just now. Notions that I say haven't yet occurred are in my future. Someone way out there will say, no, 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 that occurred just now. And therefore, the distinction that I make between past, present, and future is not a distinction that holds for all the individuals out there. So at the level of the individual, there is past, present, and future for sure. But if you lift yourself out of the perspective of the individual and consider a more global perspective, there is no organization into past, present, and future that works globally. It's all individualistic, it's all subjective. And therefore, since it's subjective, Einstein is saying in that sense, it's an illusion. It is not woven into the fundamental fabric of the world, this distinction between past, present, and future. In that sense, it is an illusion. Okay, what else do we have here? What time is it? Oh, it's 5 o'clock, but if you still want to chat a little bit further, I'm happy to do that. It's 2:36 in India. You all should sleep now, one of the viewers says. Um, some viewer, who's called viewer of all things, could a new universe spontaneously come into existence when another universe has expanded to emptiness? And yes, I mean it's conceivable that the Big Bang is an event that can happen arbitrarily many times. The required conditions for a Big Bang is to have enough uniform energy in a small enough region of space. It's usually carried by what's called the inflaton field in the conventional mathematical description. And that then yields this repulsive push that blows space to swell enormously. And in principle, quantum mechanics allows you to calculate the likelihood that such a uniform, sufficiently dense region of inflaton energy could form at any given moment. And the answer for that is a small but non-zero number. So if you wait sufficiently long, yes, you can imagine whole big bangs happening long after our universe has expanded, in the language of the questioner, expanded into what is as close to nothing as you could imagine. Okay, what else do we have? Unorthodox. What do you think of flat earthers? Well, there are truths about the world that are objective. There are truths about the world that are subjective, that speak more to our place in the world, as opposed to qualities of the world that are accessible to anybody. The earth, in the objective sense, is not flat. The earth, in any objective notion of truth, is not flat. But if someone uses the notion that Earth is flat as a metaphor that helps them to better appreciate where they fit in to the reality that they inhabit, then so be it. But goodness gracious, keep straight your metaphors and your reality. There's poetry and there are facts. And the fact of the matter is that the world has a particular objective shape. It is a sphere, as close to a sphere. It is not flat. But I'm all too happy in poetry to hear about flat Earth, in economics to hear about flattening the disparities among different places on Earth. But that's metaphor. Keep your metaphors straight, keep your poetry straight, keep it all beautiful and wonderful and insightful and subjective. Just don't mistake it for objective truth. Okay, what do we have here? Oh, T-Ball, thank you very much. Thank you. I appreciate your response to my answer. What else do we have here? Um, why does Hackers Lab asks, why does string theory require 11 dimensions of space? And the extra dimensions of string theory, particular number, is one that I have tried ever since writing The Elegant Universe to find some non-technical way of explaining that, and I really failed on that. I've never seen a non-technical explanation for why string theory requires extra dimensions. So let me give you the semi-technical explanation, which is the best that I can do. There is an equation within string theory which must vanish for the theory to be consistent. All right, that already is technical from the get-go, so I apologize for that. That equation takes the form, it turns out, a complicated expression times something really simple. So in the simplest case, it's just d minus 10, where d is the number of space-time dimensions in string theory. And so for this to vanish, The complicated thing, well, it doesn't vanish. The simple thing must, so that you have something times zero. How does d minus 10 equal zero? D equals 10. I swear to you, that's really what happens. It's a calculation in perturbative string theory that gets you to 10 as a number of space-time dimensions. To get to 11, you then realize that that perturbative calculation leaves out one dimension. This is what Ed Witten alerted us to in a beautiful lecture at University of Southern California in 1995. And so we've pieced together our understanding of 11 space-time dimensions. But I wish I could just say to you, hey, just think of a marble on a trampoline, and then give you a few more words and we get to the extra dimensions. I've never succeeded in doing that. I've never seen anyone who has. So unfortunately, I can't give you a nice non-technical explanation for the extra 11 extra dimensions. Now, Joel Jarvinen is making good reference that it goes to 11. No doubt that is a Spinal Tap reference, if I understand Joel correctly, where one of the musicians is so proud of his new amplifier, because whereas most amplifiers have a top level of 10, his amplifier has a top level of 11. So if that explanation gives you any insight, fantastic. For me, it doesn't do much beyond make me smile, but that there's nothing wrong with smiling. Aya Hassan asks, what is the use of string theory? What is the use of string theory? Well, the use of string theory is, number one, it is our most promising theoretical approach for blending quantum mechanics into general theory of relativity. So there it is. Right within string theory, the mathematics makes clear that quantum mechanics and gravity can harmoniously coexist. This is a big problem, a big challenge. What else does string theory do? Well, it shows us, at least in principle, how basically every discovery from the past 50 years in physics finds a natural home within the mathematical structure of string theory. The Higgs particle, it can fit engaged symmetries that we use to describe the electromagnetic and the nuclear forces. They have a natural home. The discrete symmetries that protect certain properties of particles, like stability of the proton, they have a natural home within string theory. On and on. String theory not only puts gravity and quantum mechanics together, but it allows all of the major discoveries of the past to also be brought within the fold. String theory is also valuable as a tool. Other subjects have found that string theory allows you to make calculations that would be horrific without the mathematical tool of string theory. So there's a great deal of use of string theory in the physical sciences, but the real question is string theory the right way to go if you want to find the deepest laws of the particles and the deepest laws that govern them? And on that, we don't know. We are still struggling to connect string theory with observations in a manner that would address that question. So there's a lot of use of string theory, a lot of mathematical use of string theory. I should have mentioned that. Some of my own work opened the door for string theory solving certain math problems that mathematicians were stumped by. And string theory can answer those questions. So on the math front, on its applications in other fields, and potentially as a unified theory of all forces and all matter. So why do we work on it? We work on it for that reason. The potential is enormous. When will we know if string theory is the right theory? Through observation and experiment? I don't have a crystal ball. I don't know. It'd be great if it was soon, but the world, universe, doesn't look to satisfy our timetable. The universe will reveal its secrets when we have the capacity to interrogate it in the right way with the right equipment. So Damon Ketterpal asks, is it resolved that free will does not exist? Any logic in favor of free will? Any good reads on the subject? Well, Damon, I'll refer you to my own thinking on this. I'll briefly describe it, but chapter 5 of my new book, Until the End of Time, it's called something like Particles and Consciousness. And it comes to the conclusion that there is no free will, at least in the traditional sense of the term. The sense that we all have, that we are the ultimate originators of our actions. We are the full author of the things that we do. That sensation, that intuition runs into problems. It runs into serious problems because when you recognize, and not everybody agrees with this. I mean, there was a review of my book that came out just the other day where the reviewer clearly does not buy into one of the key assumptions that I make, which is fundamentally the world physically is made of particles governed by laws. You don't need anything else beyond that to explain the phenomenon of existence. Now, is that absolutely true? I think it is. Many others, I'm not alone. I'm not trying to say this is an original idea, nor am I trying to point to others to bolster my position. But the fact of the matter is that many people who have thought hard about this have come to the same conclusion. There is no life force out there. There is no consciousness field that we somehow tap into. The world is made of ingredients governed by laws. And once you accept that, and you don't have to, I don't need you to accept that. I'm simply giving you a conclusion based on that way of looking at the world. Once you accept that, then free will goes out the window because we, as collections of particles, are governed by mathematical law, and the motion of our particles, therefore, is not under our control. And my dog Luna is clearly agreeing with me. One more time, Luna, let's hear you. Do you agree? The dog community agrees with no free will? No, now she's being silent. But once you recognize that your particles are under marching orders dictated by mathematical decree, and once you recognize that every choice you make, every decision you make is nothing but your particles moving one way or another inside your brain, or your body's particles moving one way or another, you don't have any choice in how those particles move. Those particles are fully governed by quantum mechanical marching orders. And in that sense, the traditional notion that you can intercede makes no sense. It's not, as I've said before, as if the laws of physics are constructed in a way, say for me, that they say, hey, particles making up Brian Greene, follow Schrodinger's equation until Brian's about to make a decision. Then hold, wait for him to make a decision. And once he makes the decision, carry out the decision that he made. No, there's no place in the fundamental laws for me to have any role like that whatsoever. So in that sense, the intuitive notion that we are these agents, volitional agents that have choices and decisions at our disposal, in that sense, it's wrong. The decisions happen, and we recognize when they happen, but we, in some sense, are pulled along by the very same laws that pull along our particles. Now, again, are there other perspectives? Absolutely. And in my book, I give some of the other perspectives. I don't think they're right. And yet, there are many opinions. And as yet, we don't have enough data to fully articulate an unassailable argument that would establish the position that I just laid out to be true. But I strongly suspect that it is true. Okay, what else do we have here? Give one that has not asked a question before. Bob Gidey asks, Dr. Greene, are quantum fields the basic building blocks of the universe? Well, our most refined and tested description of the world is in terms of quantum field theory. So it is fields that are governed by the generalization of Schrodinger's equation from particles to fields. It's the same equation, just now applied to the ingredient of fields. And fields are able to create particles. So fields are able to embrace both the more spread out quality of a field, like, an electromagnetic field, light is all spread out, but the mathematics is simultaneously able to describe the more particulate entities, the small excitations of a field. So, if you were to ask me what is the fundamental description of the world that has achieved a level of consensus because of observation and experiment, then I would agree that it is quantum field theory. And it may be that quantum field theory is the be all and end all. In fact, there's evidence that string theory is equivalent to quantum field theory, just sort of rearranges the calculations and the ingredients in a different way. So, in that sense, even string theory may be nothing more than quantum field theory. So, the answer to your question is it might be yes. Humility suggests strongly that we should be tentative and say, this is our current level of understanding. It could change 5, 10, 100 years from now. But yes, based on our current level of understanding, that's where we are. All right, let's see. I wonder if we should start to wrap this up as I'm starting to lose my voice. But let's just see what else comes in. Um, I keep forgetting to look at the Twitter list, but it doesn't seem to have been updated. Oh, I have a Facebook list. Um, so Kova Smiley from Facebook asked, if gravity can bend light, how can it not slow light down? And that is a very, very good question. And here's the answer. So when light travels, from our macroscopic perspective, we might see it traveling on some curved trajectory. And if it's going by the sun, we say the sun bends the light, bends the trajectory of the light. But if we now put ourselves actually in the shoes of the photon itself, the light itself, what it actually is doing, it's going on the straightest trajectory available to us. It goes along a geodesic in the environment. So the macroscopic global view of this curved trajectory is actually nothing but the photon traveling along the straightest path available to it, the shortest trajectory. You're sort of familiar with this. You know, on Earth, when you get on an airplane and you go over a long distance, sometimes the trajectory takes you over the North Pole or something. You're like, what in the world? Why would we be traveling along that trajectory? Your brain and your image of a flat map would suggest a different path. But actually, the shortest path, the straightest possible path on a sphere is a great circle, an arc of a great circle, and sometimes those arcs pass over the North Pole. So the light itself is not actually, from its perspective, going in a bendy way at all. Locally, it's going on the straightest possible path. So its speed locally is always equal to the speed of light. It's always going in a nice straight trajectory. It's just when you piece together all those straight trajectories from a global perspective, it looks like it went on a bent trajectory. But velocity is a local notion. It's what is its velocity at a given moment at a given location. It's always the speed of light, and it's always traveling in a straight line. Okay, what else do it? That was a good question on Facebook. Maybe another one on Facebook. They're long to read, so I'm going to go back to the shorter one on YouTube. Reckless Abandon asks about background. No, maybe Reckless Abandon is having a side conversation with Konstantinos Panagiottakis talking about background independence. He lectured by Smolin and Ravelli. So let me talk about background independence, since you guys are having you're passing notes to each other behind my back. So I'm going to jump into this background independence conversation. And this is a conversation I've had with Lee Smolin many times, and I think we see eye to eye on it. So loop quantum gravity from the get-go has this quality of background independence, which means that the equations are not tied to any given shape for space-time. They're agnostic with respect to the shape of space-time. And that's a good thing, because ideally you don't want to put space-time into your theory. You want it to emerge from your theory, and loop quantum gravity promises that from the get-go. In string theory, the way we have developed the theory is in what's known as perturbation theory. And that's now, we've gone beyond that with certain developments in the last decade or so. But let me just go back to the beginning as it's easier to describe. So, we initially described string theory in terms of small fluctuations about a given background. And therefore, the claim was made that string theory is not background independence. You sort of got to give the shape of space time. And then gravity amounts to little tiny ripples imposed on that pre existing shape for space time. So there was a conversation that was happening for a while that loop quantum gravity is background independent and string theory is not background independent. But the fact of the matter is, in our understanding of string theory, we can arbitrarily perturb that background, get to a different shape, and then talk about gravitons as little fluctuations about that new background. So, what I like to say is string theory in that formulation doesn't have manifest background independence. There is a background in our description, but the equations are sufficiently general that they are amenable to an arbitrary change of that background. So while they don't have manifest background independence, they do have as much background independence as they possibly could, given that perturbation theory needs you to specify a background around which to perturb. Developments more recently that have given us more non-perturbative formulations, the ADF-CFT correspondence allows us to speak in a manner that's more general than the one that I just gave, but the conclusion is the same. String theory is as background independent as it possibly could be expected to be. Okay, hopefully that helped in clarifying that side conversation that you all were having. Let's see what we have here. Pyotr asks your thoughts on the graviton. Does it exist? I think it probably does exist. I don't know if we're ever going to detect an individual graviton. Again, gravity is an incredibly weak force. It is, depending on you measure it, something like 40 orders of magnitude weaker than the electromagnetic force. If I had, say, two electrons repelling each other, the strength of that electromagnetic repulsion would be 40 orders of magnitude or sort of larger than their gravitational attraction. Gravity is just really weak. And a graviton is the smallest packet, the smallest bundle of this spectacularly weak force. So to find the smallest part of the weakest force is a huge experimental challenge and not one that I anticipate anytime soon that we will overcome. But do I think that the graviton is real? Yeah, I do. Okay, what else do we have here? Reckless Abandon came back at me. That's always fun. But now it ran away. I think I knew what it says. I think the question was, doesn't the background that you select around which you perturb, doesn't that define a vacuum state? And yeah, it does. So for any given geometrical shape, there is a vacuum state. My point is that string theory, the equations are not really tied in any fundamental way to that shape because you are able to perturb arbitrarily far away from that shape. You have the same darn equations. Then you can consider small fluctuations, say to talk about a graviton, about that new vacuum state. So the dependence on the background is not a string theory dependence per se. It's a perturbation theory dependence. It's the way you're analyzing the theory as opposed to an intrinsic limitation of the theory. That's the point that I am making. Arpit Tech says, can you finish the Q&A because I need to go to sleep? What I will tell you, Arpit Tech, I give you permission to go to sleep. You're not going to miss anything. Well, you may. You know what? On second thought, Arpit, no. If you want to really hear everything that's going to happen here, you better stay awake for just another few minutes. I'm gonna wrap this up pretty soon. I always like to wrap it up on a high note, some question that it just sort of blows me away. And let's see what we can do to get to that. Well, here's a good one, a frequent one. But Fatima Sayed Hassan asks, "Where does the universe expand?" And I presume what that means is sort of what does the universe expand into? Again, it's a natural way of thinking about things based upon everyday experience. Man, it's getting pretty sunny in here. Um, Boy, and I don't have any window shades, but whatever. So I probably look like I'm in the witness protection program. Probably half of my face is bright and half is dark. But when you think about anything expanding, right? When you think about a balloon expanding, when you think about bread expanding, it's always expanding into a pre-existing space. And therefore, you naturally imagine that when the universe expands, it too must expand into a pre-existing space, sort of some real estate that the universe has somehow not yet occupied, not yet claimed hegemony over. It must expand into that. And that may not be right. And the traditional way of thinking about the expanding universe is not right. We imagine that as the universe expands, it creates the very space that it expands into. That space wasn't there before the expansion. The expansion is literally the creation of new space, new territory. And the universe inhabits it by virtue of the fact that that territory came into being because the universe expanded. It's not that it expanded into it, it expanded by virtue of creating it. That's the difference in thinking about the expansion of bread and the expansion of the universe. Okay, what else do we have? Um, Anas Abu Salam asks, could the universe have begun as a black hole? Yeah, I mean, Lee Smolin was mentioned earlier, and Lee has an interesting theory that black holes give rise to other universes. In some sense, the interior of a black hole opens up into a new realm. And he has an interesting notion of natural selection among universes, namely that those universes that have constants changed in just the right way to maximize the production of black holes, thereby producing more universes, more children, more progeny, are the ones that are better adapted and therefore will dominate reality. So he makes a prediction that the typical universe in this ensemble should be one whose parameters, masses of particles, strengths of forces, are finely tuned to maximize the production of black holes. You know, you want to have a lot of kids in order that you dominate the Darwinian evolution. The universe wants to have a lot of extra universes produced in order that it dominates that competition. And the way it dominates it in this perspective is by having a lot of black holes. So, yes, it's possible. I don't know. I've never been convinced of that idea. It's an interesting, it's very creative. So, I'd like the idea a lot. But I am not convinced that there's any real data that allows us to fully talk about how a universe would emerge from a black hole, nor how the constants of nature would change as you pass through a black hole. A lot of details that have yet to be nailed down before I would take that picture seriously. Okay, so what do we got? Andre Konofsky, how can one get into string theory after grad school? I would say get into string theory during grad school if you could. I mean, I think that's a good way of going about it. Past grad school, what can you do? Sure. I mean, people change fields all the time. Getting into string theory is more of a challenge because it's the most highly mathematical of all the theoretical pursuits that you might have undertaken. And that means you'll have to learn more and more stuff that you could have learned as a grad student, but you probably didn't if you were studying a different field. Not impossible to do, can be difficult to do. Andrew Haney asks, what is energy? And Multiplier Fan says, do you love me? I'm not sure which question to answer first. So I think I'll just answer one of those. What is energy? So, energy is a very subtle idea. We throw the word energy around all the time. In basic physics class, you learn energy is anything that has the capacity to do work. Work is moving an object through a distance, right? So I'm exerting energy to move an object through a distance, a force exerted through a distance. And I find that's not a bad way of thinking about things, but I think having an inventory of energy gives you a feel for it. So, mass is a kind of energy, motion is a kind of energy, kinetic energy is a kind of energy, compress a spring or stretch a spring, potential energy is a kind of energy. Energy from gravitational potential, you see its energy, it can be turned into motion. So once you sort of have at your disposal some of the examples of energy, now you can say energy is anything that I can acquire from those ingredients through an allowed physical transformation. Potential energy to kinetic energy, nuclear situations where we can take energy that's strong, that's in the strong nuclear force, and turn that into kinetic energy. So it's basically anything that has the capacity to impart motion. Okay. What else do we have here? Stosh asks, Stosh, I like your question. Genetic, plasma, nuclear energy, all types of energy. Okay, thank you. Piping in on that. Piotr asks, maybe this is a good one to end on. Piotr asks, what is life? And and again, it's a question that you can gain insight into by taxonomy, by giving a listing of examples of life. Right? You look, your question, genetic, plasma, nuclear energy, all types of energy. Wait, why am I hearing myself talking? Oh, your turn. Oh, now I'm having, maybe this is a sign that I should go off. I'm hearing myself talk. What is life? Yeah. What did I do wrong? Did I hit a button? Can I mute myself? Or should I sign off? Is this the sign from the gods that I should give up? Oh, I don't have any feedback anymore. All right, I think we're good. Do you guys still hear me out there in the YouTube world, or am I now talking into the void? Let me know if you can still hear me, and also let me know if you want me to wrap this up. It's 5:39. I figure I could go for a few more minutes if you want. It's still light out here, and I'm not going to do this in total darkness, although I do have some lights on in here too. But what was I talking about? What is life? Let's see where that takes us. So there's some examples of life, right? Human being, dogs, cats, bees, insects, birds, dinosaurs, right? So having the taxonomy in mind is useful to thinking about life, but it's notoriously difficult to give an ironclad definition of life. I think the definition that was on one of the spacecraft that had, the recording of sounds of planet Earth described life as, I think, anything that had the capacity to carry out Darwinian evolution by natural selection. I don't know. I don't know if that really helps you get a feel for life, but life is anything that can carry out the processes of life. It's kind of circular, but life is anything that can move. It's something that can metabolize, right? It can take in ingredients from the world and turn them into energy to power internal physical processes. So, there are all sorts of criterion that you might put out for the Venice. Man, there's all sorts of stuff happening. Now there's an alert happening on my phone. There's a tornado coming. Seriously, you guys see this? I may have to sign off if the tornado comes. Yeah, the sky is turning kind of dark, but I think I'm in a relatively safe spot. But anyway, if you see me swept away by a tornado, you know that I have gone to the land of Oz or something of that sort. But yeah, the forces are seeming to tell us to wrap it up, and I'm going to soldier on. But my point is, there are many boxes that you can tick, such that a living system satisfies the criteria in your list. But I really do think that life is a continuum. It's not that life is something that satisfies this list of criterion. Rather, if it does satisfy this list of criteria, then you can call it life. But if it doesn't mean that it's not life. It might mean that it is en route to the kind of life forms that we are more familiar with. But I think that life extends all the way back. And at some point, in the Darwinian evolution, you get to a level of complexity and refinement where it's obviously a living system. But I don't think there's a place where you can say that life turns on. Life is organized complexity. Life, I like to say, is physics orchestrated. And if that orchestration has sufficient robustness and complexity, then you have a living system. And when it doesn't quite have that, you are en route and perhaps better thought of as being along the spectrum that goes from inanimate to animate, not something that necessarily turns on like a light switch. All right, guys. The wind is really picking up here, and I see all my family heading inside, and they're probably going to bar the doors if I don't get in there in time. So I think I'll probably wrap it up here, unless there's like one more question that I just have to answer. And I'm scrolling through. Oh, Kent Linkletter asks, is a Boltzmann brain alive? Well, yeah, I would say that in relation to the question that we just had, if you had a Boltzmann brain out there in the void, able to carry out even momentarily the processes that this gray thing inside of our head does, and if that brain, has the thoughts that, for instance, match my own, if its particulate arrangement happens to mimic and replicate the particle arrangement in my head right now, I think I would absolutely call that Boltzmann brain alive. And after all, if I was able to grab that brain and stick it inside a human body and connect it up appropriately, that brain would function precisely as an ordinary human brain. So I would certainly characterize it as a living system. It might not live long without the life support that a body and a planet can provide. But during the moment of cogitation that that brain carries out, yeah, I would say it is a living system. Okay, so people are telling me to stay safe. I appreciate that. Please go to the shelter. I'm going to do that. All right, guys. So this has been fun. A little shorter than perhaps we would have if the situation hadn't changed. Next week, maybe we'll go for an even longer marathon session. Until then, watch until the not until the end of time. That's my book. I mean, take a look at your daily equation videos. Catch up on any that you've missed. Let me know. I swear I don't know the level of rigor that you want, because sometimes I'm more technical than other times, and it seems like less people are engaging with those. But maybe it's just a small core of you diehard mathematically rigorous people, and that's a fine thing too. I don't need to reach a lot of people with these as long as I'm reaching people for whom they matter. But I'm gonna have a blend, of general ones and more specific ones. As I've said always, I'm not sure how long I'm going to carry on doing the series. I actually have to teach a course at Columbia starting May 26th. Hey, any of you, you're allowed to sign up for the course. Unfortunately, it is pretty darn expensive. It's what universities do. They have a lot of expenses, so it's not cheap to sign up for my course. But it is on my book until the end of time. It's called Origins and Meaning. You can search under Columbia Summer School if you want to do that. I'd love to see some of you in that. But again, unfortunately, I've got no control of this. It does cost a little bit of money, or a lot of bit of money, to do that. Once that course begins, it may be harder for me to do your daily equations. So toward the end of May, I may look to wind this down. Maybe I'll call it your weekly equation if you don't mind. Maybe do some videos once a week and some live sessions once a week. That's a possibility. But go check it out. Check out the Columbia thing if you're interested. Check out your daily equation if this is new to you, if this is your first engagement with this. And until my next video, I hope to do it on Monday. What am I going to do? I don't know. I think I may do something in cosmology. Maybe I do the Big Bang, or maybe I'll do dark energy. That'd be fun to do. Tell me what you'd like me to do on Monday. If I see something in your list, I will do my best to accommodate it. Okay.